Hi everyone, this is MathsForUni. Today I'll be looking at question 7 from lecture 12 of our Udemy course, Bridging the Gap to Maths at University. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. The question says, consider f of z a complex valued function of the variable z equals x plus iy. If we decompose f of z into real and imaginary parts, then we have f of z being u of xy, the real part, plus I v of xy, where v is the imaginary part. Then, providing certain conditions are satisfied, the Cauchy-Riemann equations tell us that necessarily the following must hold. du dx is equal to dv dy, and du dy is equal to minus dv by dx. The question is to verify that this is true for f of z equals z cubed. So we begin by decomposing this f of z into its real and imaginary parts. We write z equals x plus iy, and then we have f of z equals z cubed, which is x plus iy, all cubed. And then by expanding with the binomial formula, we will have x cubed plus 3x squared iy plus 3x and then an iy squared and then an iy all cubed. Then, separating the real and imaginary parts, we will have x cubed, and then we'll have a minus 3xy squared from this term, and then the other terms will have a factor of I in them. We have a 3x squared y with the I in that one, and then we have a minus iy cubed because I squared is minus 1. So if we write f of z as being u of xy, the real part, plus I v of xy, the imaginary part, then we identify u of xy as being x cubed minus 3xy squared, and v of xy as being 3x squared y minus y cubed. Then we want to check that the so-called Cauchy-Riemann equations hold for this example function. So we want to check these equations here. As a result, we need to calculate the partial derivatives of u and v with respect to x and y separately. So we start by looking at du by dx, for example. This will be 3x squared minus 3y squared. Then we can do du by dy, which gives us minus 6xy. Next we look at v, so dv by dx is 6xy, and then dv by dy is 3x squared minus 3y squared. So indeed, these two things are equal, and these two things are equal up to a minus sign. So we have du by dx as being equal to dv by dy, and du by dy up here is equal to this but with a minus sign, so equals minus dv by dx. As a result, for this function, the Cauchy-Riemann equations are satisfied. Let's now take a look at another related question on the Cauchy-Riemann equations. So this question is question 8 from the same lecture, and it says, given the Cauchy-Riemann equations introduced in question 7, show that u and v are harmonic. And it says that a function g of xy is harmonic if we have this condition here for g. We differentiate g twice in x and twice in y, add them together and get 0. So we begin by assuming that we have some complex function f of z with real part u of xy and imaginary part v of xy, and then the Cauchy-Riemann equations for u and v tell us that du by dx equals dv by dy, and du by dy equals minus dv by dx. We want to show that u and v are harmonic. So we need to show that, looking at this equation here for g, d squared u by dx squared plus d squared u by dy squared is equal to 0, and the same for v as well. Let's take a look at the equation for u first. Let's consider this expression here and try and show that we get 0. So d squared u by dx squared plus d squared u by dy squared is equal to d by dx of du by dx plus d by dy of du by dy. This is what it means to differentiate a function twice with respect to one variable. We do it once with that variable and then again. Now we can use the Cauchy-Riemann equations. We can take du by dx and replace it with dv by dy, and the same with du by dy, giving us a minus dv by dx. So by Cauchy-Riemann, we get d by dx of dv by dy, and then plus d by dy, and then a minus dv by dx. Then putting this back into normal differentiation notation, we get d squared v by dx dy, and then a minus from this minus here, d squared v by dy dx. This is equal to 0 because of the symmetry of mixed partial derivatives, as we discussed in the last video. Therefore, we have that u is harmonic. Next, we can do the same for v, but let's go through it slightly faster. D squared v by dx squared plus d squared v by dy squared, we want to show is 0, but it is d by dx of dv by dx plus d by dy of dv by dy. Then the Cauchy-Riemann equations give us d by dx, and then a minus du by dy, then a d by dy, and a du by dx. This is equal to minus d squared u by dx dy plus d squared u by dy dx, which is again 0 by the symmetry of mixed partial derivatives. So therefore, v is also a harmonic function. If you found this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. Thanks for watching, and goodbye for now.